was not supposed to look like this, not this early, not this far away. And yet there it was, frozen in the dark. A giant galaxy with no clear spin at all. Scientists were stunned the moment the numbers came in. Because if this one object is real, and it is, then a rule we trusted about the young universe may have broken long before anyone thought it could. Stay with this story, because the final piece is the one that makes the whole picture feel even stranger. 12 billion light years from Earth, in a part of the sky that had already been studied many times, the James Webb Space Telescope took a closer look at a massive ancient galaxy called XMM Vid 12075. The light Webb captured from it began its journey when the universe was less than 2 billion years old. That means this was not a look at what the galaxy is now. It was a look at what it was when the cosmos was still incredibly young, still learning how to build its first great structures. And that is exactly why this discovery matters so much. When astronomers talk about galaxies, spin is almost always part of the story. A galaxy is not just a bag of stars floating together. In most cases, those stars move in some organized way. Spiral galaxies are the easiest examples to picture. Their stars sweep around the center in a broad, graceful turn, forming the kind of structure you see in the Milky Way and Andromeda. Even if a galaxy is not a neat spiral, astronomers still expect its history to carry some trace of motion, some memory of the way gas fell inward and gravity shaped the whole thing over time. That expectation comes from a basic rule of physics. When clouds of gas collapse, they tend to keep their motion. They tighten, they speed up, they begin to rotate. It is the same idea you see when a skater pulls in their arms and spins faster. On the largest scale imaginable, that same rule helps explain why galaxies form the way they do. So finding a huge galaxy that had already gone quiet, already stopped making new stars, and showed no clear organized rotation so early in cosmic history was not just odd, it was deeply unsettling. Ben Forrest and his team used Webb to study this galaxy and compare it with two other massive galaxies from a similar era. That part matters. Scientists were not looking at one blurry dot in isolation and guessing. They were testing a sample. One of those galaxies showed the kind of rotation you would expect. Another looked messy, like a system still being built. But XMM Vid 12075 stood apart. Its stars did not appear to be moving in a clean, rotating disk. Instead, the motion looked random, more like the giant, slow-moving elliptical galaxies we see much later in the history of the universe. And that raises the question that hangs over everything in this story. How did a galaxy this young become so old in its behavior? To feel the weight of that question, you have to picture what astronomers thought the early universe should be like. Not calm, not polished, not settled. The early universe should have been noisy, rough, crowded, full of collisions and frantic starbirth. Young galaxies were expected to be smaller, less organized, and still in the middle of becoming themselves. In that picture, you do not get a massive, dead, slow-moving giant so quickly. There simply should not have been enough time. But here is where things start to turn. XMM Vid 12075 was not some tiny failed galaxy at the edge of detection. Earlier observations had already shown that it was enormous, with several times the stellar mass of the Milky Way. It had also already shut down most of its star formation. That alone made it unusual. Then Webb did what ground-based telescopes struggle to do at such extreme distances. It let scientists probe the internal movement of material inside the galaxy itself. That is the kind of detail astronomers usually get for nearby galaxies, not for objects that existed when the universe was still in its first chapters. Think about that for a second. Webb is not just showing us older things. It is showing us older things with enough clarity to ask a much harder question. Not only what is that object, but how is it behaving inside? And for this galaxy, the answer was unsettling. It looked like a system that had already been through the kind of history astronomers usually expect to take much longer. Now, if you were one of the scientists seeing that result for the first time, what would you assume? Would you trust the data right away, or would you hunt for the flaw that had to be hiding somewhere? Because that is what often happens when the universe gives an answer that feels too early, too large, or too clean to be real. At first, the easiest response is doubt. Maybe the signal is misleading. Maybe the object is being distorted. Maybe we are seeing some temporary effect. Maybe the internal motion is harder to measure than it looks. But Webb's power is exactly what makes that kind of escape route harder now. This telescope sees ancient infrared light with a sensitivity older missions simply could not match. Light that started in the visible range billions of years ago has been stretched by the expansion of space itself. By the time it reaches us, it has slipped into infrared. Webb was built for that world. And that is why discoveries like this hit so hard. They're not just dramatic headlines. They come from a machine designed to test the early universe at the level where hidden assumptions begin to fail. The more you look at XMM Vid 12075, the stranger it gets. In the nearby universe, galaxies with little organized rotation do exist. Astronomers call many of them slow rotators. But those are usually massive, mature systems seen much closer to our own time. They are often thought to have lost their orderly motion through long histories of mergers, one collision after another, over billions of years. Imagine a once neat spinning system being bumped, twisted, and remade so many times that the original spin becomes scrambled into random motion. That is a believable story for an old universe, but for a young universe, it feels rushed. Too rushed. And that leads to the next possibility, the one that makes this story feel almost violent. Maybe this galaxy did not slowly lose its spin through countless smaller encounters. Maybe something much more direct happened. Maybe two galaxies crashed into each other in a way that nearly erased their rotation in one brutal event. If the motion of the two systems opposed each other strongly enough, the result could be a galaxy whose stars no longer move in a clean shared direction. Instead, the motion would look scattered, broken, almost as if the system had forgotten how to turn. That is not just a dramatic idea. Forrest's team saw an extra glow of light off to one side of the galaxy, a lopsided feature that may point to an interaction. Something may have come in from the side. Something may have slammed into the system hard enough to change its whole internal story. And if that is true, then the mystery becomes even sharper. Because now the question is not only how this galaxy lost its spin, it is how the early universe managed to create the conditions for such a major event so quickly. This is the point where a lot of people imagine astronomy as a slow, distant science, full of careful numbers and cold language. But the truth is, moments like this are emotional. Somewhere behind those papers and data tables are people looking at a result and realizing the universe just pushed back. A model that felt solid a week ago suddenly feels thinner. A timeline that seemed safe becomes harder to defend. And nobody says it out loud at first, but everyone is thinking the same thing. What if this is not a one-off? Because a single strange object can always be treated as an outlier. A curiosity, a fluke, an edge case. Science can absorb one shock. It does that all the time. But a pattern is different. A pattern forces a reckoning. And Webb has been building that pattern almost from the beginning. Not long after the telescope started sending back deep field images, researchers reported several candidate galaxies from just 500 to 700 million years after the Big Bang that appeared shockingly massive. Some estimates suggested populations of stars on the scale of the modern Milky Way, and maybe more, packed into systems that seemed far too mature for that era. One researcher called the result bananas, which is about as honest as scientific language gets when nature refuses to behave. These were not comfortable findings. The standard picture of early galaxy growth says the first galaxies should begin small and then slowly build up. But in these Webb images, astronomers were seeing objects that looked bright, red, and heavy very early on. That does not automatically mean the models are wrong. There are always caveats. Some of those objects might turn out to hide active black holes. Some masses might shift after better spectra. Some assumptions about their light might need revision, but even with all that caution, the signal was hard to ignore. Something in the early universe was growing up fast. And then came another strange class of objects. Tiny, red, compact, common enough to become their own category. Astronomers started calling them little red dots. The name sounds almost harmless. It should not. These things became one of the most puzzling Webb discoveries because nobody could agree at first on what they really were. At a glance, they seemed like they might be young galaxies, but many were too bright and too compact for simple explanations. Then, spectra and follow-up work began pointing in another direction. Some of these dots appeared to host feeding black holes wrapped in thick cocoons of gas. Instead of ordinary galaxies breaking cosmology, they may be black hole-powered systems wearing disguises. If you want a perfect example of why the Webb era feels so unsettling, this is it. First, the telescope seems to find objects too massive too early. Then the story gets more complex. Maybe some are not mature galaxies after all. Maybe some are black holes hidden inside dense envelopes that change how their light looks. In other words, the early universe may be even stranger than the first shocking headlines suggested, but not necessarily in the same way. And that matters for our spinning mystery too. Because XMM Vid 1 2075 sits right in the middle of that larger Webb pattern. Again and again, the early universe is giving us systems that look more developed, more extreme, or more specialized than many astronomers expected. Not always impossible, not always revolutionary on their own, but surprising enough, often enough, that the old comfort is gone. Let me ask you this. If the universe keeps doing this, do we say the model is broken, or do we say we are finally seeing parts of the model we never had the tools to test before? That is a real divide inside the drama. Not a fight between science and doubt, but a fight between two kinds of scientific caution. One side says, slow down, better data will probably reduce the tension. The other side says, maybe, but the pattern is getting too consistent to shrug off. And now we arrive at the turn in the story, the part that changes the mood completely. Because a non-rotating galaxy is strange enough by itself. But once you place it beside Webb's other early discoveries, it stops looking like an isolated oddity and starts feeling like a warning light. Take those massive early candidates. If even some of them are truly as heavy as they first appeared, then galaxies assembled more quickly than expected. Take the little red dots. If some of them are black holes wrapped in dense gas, then black hole growth in the early universe may have been happening in forms we barely anticipated. Take the record-setting galaxy JWST Z13-1, seen only about 330 million years after the Big Bang. Webb detected a bright Lyman alpha signal from it, a kind of hydrogen light that should have struggled to escape through the thick neutral fog of the early cosmos. That means either the region around it had already been cleared more than expected, or the sources inside it were far more powerful or unusual than many models assumed. Piece by piece, the young universe looks less like a simple nursery and more like a battlefield of fast growth, hidden engines, and rapid change. That is what makes XMM Vid 1-2075 feel almost frightening. It is not frightening in the movie sense. It is frightening in the scientific sense. It hints that the early universe may have been able to produce finished-looking outcomes at a speed we still do not fully grasp. And if that is true, then the central mystery becomes much bigger than one silent galaxy. How many other systems out there grew up too fast, collided too hard, or shut down too early for our old timelines to explain? This is the emotional peak of the whole story, not because we found one bizarre object, but because the object seems to whisper the same thing Webb has been whispering for years now. The first chapters of cosmic history may have been more aggressive, more efficient, and less orderly than we imagined. Picture the scene. A giant galaxy already packed with stars, its star-making days mostly over, its internal motion scrambled, its light crossing 12 billion years of expanding space only to reach a species that, until very recently, had no instrument capable of reading the message properly. And that message is not subtle. It says the universe was experimenting earlier than we thought. But here is where we need to be careful. Awe is not proof. Drama is not data. Astronomers know this better than anyone. They have seen exciting claims soften before. They have seen early interpretations get corrected. That is why no serious scientist looks at one strange galaxy and declares the whole framework dead. That is not how this works. Instead, they compare. They simulate. They ask how rare such an object should be. They look for more. For XMM Vid 1-2075, some simulations do allow a very small number of non-rotating galaxies this early. So this discovery does not automatically overturn everything, but it raises the stakes. If more galaxies like this are found, then rare becomes common, and common becomes a problem models must solve. That is the line scientists are now watching. And this is where expert reaction becomes so interesting. The language is cautious, but the surprise is real. Forrest described the lack of rotation as surprising and very interesting. Other researchers working on early massive galaxies have used even blunter language when Webb returned systems that looked far too mature. They expected tiny baby galaxies. They found objects that seemed almost grown. They expected simple questions. The universe handed them much stranger ones. There is also a deeper debate hiding underneath all of this. Are we seeing problems with cosmology itself, the large-scale story of how matter gathered after the Big Bang? Or are we mainly seeing gaps in our models of star formation, black hole growth, dust, and feedback in the early universe? That difference matters. One possibility says the grand map is mostly right, but the details of early galaxy evolution are messier than expected. The other says some of the large assumptions in the map may need revision. Right now, the honest answer is that nobody knows for sure. And that uncertainty is not a weakness. It is the story. Science becomes most alive when the evidence outruns the script. Webb has done that again and again. It has not destroyed modern astronomy. It has made astronomy work harder. It has forced theories to face a universe with sharper detail. That is what powerful instruments do. Hubble did it in its time. Webb is doing it now, only deeper, earlier, and in some ways more painfully. Think about the little red dots again. At first glance, they looked like impossible early galaxies. Then stronger evidence suggested that at least some may be dense black hole-powered sources. In one recent case, NASA highlighted a little red dot called Glimpse 1775 and said the evidence strongly supports a black hole surrounded by a hot, dense gas cocoon. That kind of result does not close the mystery. It refines it. Instead of saying the early universe made giant normal galaxies everywhere, it says some early systems may have been powered by hidden black holes that change how we read their light. That is not less exciting. It may be more exciting, because it means the universe was not only building stars fast, it may also have been building powerful central engines in forms we did not expect. And once you accept that, XMM Vid1 2075 becomes more than an isolated puzzle. It becomes part of a young cosmos that may have been full of extreme pathways. Some galaxies spin up neatly, some remain chaotic, some grow black holes behind curtains of gas. And at least one massive system we know about seems to have reached a slow rotator state almost unbelievably early. So what happens next? Astronomers search for more examples. That is the only answer that matters. One case inspires debate. A sample changes the field. If Webb uncovers several more ancient slow rotators, then theorists will need to explain how major mergers, rapid mass assembly, and star formation shutdowns happened so efficiently so early. If those galaxies remain extremely rare, then the standard picture may bend without breaking. Either way, the search itself becomes one of the most important tests of how the first giant galaxies really formed. And before I go further, think about this for yourself. If you could watch one missing chapter from the history of the universe, would it be the birth of the first stars, the feeding of the first black holes, or the collision that may have knocked this galaxy out of spin? Put yourself there. Because what comes next pulls all three of those questions into the same larger mystery. The bigger picture is where this discovery stops being just about astronomy and starts feeling almost personal. Human beings have always wanted a clean origin story. We like to imagine the universe unfolding step by step, each part arriving on schedule. First the dark, then the first stars, then small galaxies, then larger ones, then structure, order, complexity. A sensible chain, a calm progression from simple to grand. But the deeper we look, the less calm it seems. Maybe the early universe did not wait politely for structure to mature. Maybe it ran hot. Maybe it built giants in bursts. Maybe black holes rose behind veils of gas while the first galaxies were still learning their shapes. Maybe some regions cleared the cosmic fog faster than expected. Maybe catastrophic collisions happened in places where our neat timelines said there had barely been time for introductions. That possibility changes how you feel about the night sky. Because when you look up, you are not only seeing distance, you are seeing history. Every faint point is a delayed message, and Webb has begun opening messages that were sealed for more than 13 billion years. Some of them tell us what we hoped to hear. Others tell us we may have been asking the right questions with incomplete imagination. There is something beautiful about that. The universe is not obligated to match the first draft of our understanding. In fact, the most important discoveries often begin when it does not. A galaxy that should have been spinning is not. A source that should have been hidden shines through the fog. Tiny red dots turn out to conceal possible black holes. Massive systems appear earlier than expected. None of this means everything we know is wrong, but it does mean the frontier is real. We are not just filling in blanks. We are still discovering what kind of story the universe actually is. And maybe that is the deepest reason discoveries like XMM Vid1 2075 grip us so hard. It is not only the physics, it is the feeling that reality is still larger than our best summary of it, the feeling that somewhere in the dark, long before Earth existed, processes were unfolding with a speed and violence that even now we are only beginning to recognize. So return to the first mystery one last time. How did a giant galaxy stop spinning so early? Maybe a violent merger canceled its motion. Maybe extreme early growth made such systems possible sooner than expected. Maybe there are more out there waiting to be found, hiding in Webb's deep fields like forgotten chapters. We do not have the final answer yet, but we do have something almost as powerful. We know the question is real, and that matters because questions like this are what move science forward. They force new observations, they sharpen theories, they humble certainty. One day, there may be a cleaner explanation. Maybe this galaxy will fit into a revised model so well that future students will wonder why anyone was shocked. That happens in science too. Today's impossible object becomes tomorrow's textbook example. But we are not there yet. Right now, we are still inside the moment of surprise. Right now, we are still watching Webb peel back the earliest layers of cosmic time and show us that the young universe may have been stranger, faster, and more dangerous than we imagined. And if that thought stays with you, it should. Because out there, beyond the reach of any human ship, beyond even the old reach of Hubble, the universe has been keeping its first secrets in infrared silence for billions of years. Webb is finally hearing them. And one of those secrets is a galaxy that seems to have lost its spin before the cosmos was ready. If you want to keep following mysteries like this, the kind that make even scientists stop and stare, stay with Galaxy Sphere. And tell me what you think in the comments. Was XMM Vid1 2075 a rare cosmic accident? Or is it the first sign that the early universe was rewriting the rules from the very beginning? James Webb just found a galaxy that should still be spinning. This ancient Webb discovery may change. What we know about early galaxies, scientists weren't ready for what Webb saw. 12 billion light years away,